Hey everyone, and welcome. Today, we are diving deep into a chapter that can feel a little intimidating at first, relations and functions. But I want you to forget about lectures and textbooks for a bit. Instead, think of this as a detective case. We're on a mission to gather clues, follow the evidence, and by the end of this, I promise, we're going to crack this case wide open. All right, detectives, every good investigation needs a solid plan, right? So here's our roadmap. We're going to start by building a quick bridge from stuff you already know. Then we'll define our main suspect, the relation. After that, we'll learn the 3 key clues we need to look for. We'll solve the special equivalence case, and then we'll put all our new skills to the test with some real detective work and a few advanced takeaways. Okay. So before we jump into any new territory, a good detective always reviews the old case files. So let's take a quick moment to build a solid bridge from what you learned back in class 11, starting with the absolute bedrock of this entire topic. And that bedrock is the Cartesian product. Now I know, the name sounds super technical, like something out of a sci-fi movie, but the idea is actually incredibly simple. Just imagine you have 2 sets, A and B. The Cartesian product is just the complete list of every single possible pairing you can make, grabbing one thing from set A and one thing from set B. That's it. It's the whole universe of possibilities we're going to be working with. Now here's our first, really crucial piece of evidence. In this world of ordered pairs, order is everything. The pair 1-3 tells a completely different story than the pair 3-1. As you can see right here, A times B and B times 8 give you totally different lists of pairs. This isn't just a minor detail, it's a fundamental rule of the game, so keep it in the back of your mind. So we've got our universe of all possible pairs. How do we get from there to the main event? Well, what is a relation really? Turns out the answer in math is surprisingly close to how we think about relationships in our actual lives.
Seriously, think about it. You've got all kinds of relationships, right? With your parents, your friends, your siblings, and every single one of them needs 2 parties involved. And, this is the important part, a specific rule that defines that connection. Is the parent of, is the friend of, is the sibling of. It's that rule, that definition, that gives the whole thing meaning.
And that idea translates perfectly into math. Every single relation is built on these 3 ingredients. You need a starting set, A. You need an ending set, B. And then you need the rule, the specific condition that decides which elements from A are actually allowed to connect to elements in B. And here it is. This is the big secret. A relation is not some scary new thing. It's just a selection of pairs, a subset that we pull out of that giant universe, the Cartesian product. We look at all the possibilities, and we only keep the ones that follow our specific rule. That's all a relation is. Okay, now we're getting to the heart of it. To really investigate a relation and figure out what it's all about, we need to check for 3 specific properties. These are our key clues. This is the detective's toolkit, and they're called reflexive, symmetric, and transitive. Our first clue is the reflexive property. The motto here is simple. Everyone relates to themselves. Now, the key word here is every. To check for this, we have to look at our starting set A, and for every single element in that set, we have to ask, does its doublet, its pair with itself, like AA, exist in our relation? If our set is 1, 2, 3, we need to find 1, 1, and 2, 2, and 3, 3. If even one of them is missing, boom, it's not reflexive. Our second clue is symmetry. And here, you have to really pay attention to the if-then logic. It doesn't mean every pair has to be reversed. It means if you find a pair like, say, 1, 2 in your evidence, you are then obligated to go hunt for its mirror image 2, 1. If you find the first one, but the second one isn't there, you've got a problem. It fails the symmetry test. And finally, our third clue, which is usually the trickiest one, is the transitive property. The best way to think about this is like connecting the dots. The rule says, if you can find a path from A to B, which is the pair AB, and you can find another path from that same B to some new element C, which is the pair BC, then you absolutely must be able to find a direct shortcut from A all the way to C, the pair AC. Now, don't worry if this one feels a little fuzzy right now. It's kind of like the slow burn mystery plot of this whole chapter. You know, like in a great thriller movie, you see all these little pieces that don't quite connect at first. But trust me, once we start using this to solve some actual problems, a light bulb is going to go off and it'll all click into place perfectly. So what happens when we're investigating a relation and we find all 3 clues? What if it's reflexive, and it's symmetric, and it's transitive? Well, that's when we know we found something really special. we've cracked the big case. It's called an equivalence relation, and you can think of this as the grand prize of our detective work. When a relation has all three properties, it means it's perfectly balanced and consistent. Everyone relates to themselves, all relationships go both ways, and all the chains of connection are complete. It's a really neat and tidy structure in mathematics. Okay, theory time is over. We've got our toolkit, we know the clues. Now it's time to get our hands dirty and actually apply this stuff to some real exam-style cases. This is where it all comes together. But before we start, you need to remember this one killer shortcut. I call it the gotcha rule, and it's your secret weapon. To prove that a relation is not something, not reflexive, not symmetric, not transitive, you don't need some long, complicated proof. All you need is to find one single example that breaks the rule. One piece of evidence is enough to say, gotcha, and move on. Okay, here we go. Case number 1. Our set has the numbers 1 through 14, and the rule for our relation is 3x minus y equals 0. That's just a mathy way of saying y equals 3x. So let's figure out what pairs are actually in our relation. Well, if x is 1, y is 3. If x is 2, y is 6. If x is 3, y is 9. And if x is 4, y is 12. And that's it, because if x is 5, y would be 15, which isn't in our set. So our evidence is 1, 3, 2, 6, 3, 9, and 4, 12. Now let's test it. And this is a perfect example of the gotcha rule in action. Let's check our clues. First, is it reflexive? Let's just check the number 1. Do we have the pair 1, 1? Well, is 3 times 1 minus 1 equal to 0? Nope. Gotcha. It is not reflexive. Done. Next, symmetric. We know the pair 1, 3 is in our relation. Is its reverse, 3, 1, in there? Well, is 3 times 3 minus 1 equal to 0? No way. Gotcha again. Not symmetric. Finally, transitive. We have a chain here, right? We have 1, 3, and we have 3, 9. So we must have 1, 9. Let's check. Is 3 times 1 minus 9 equal to 0? Not even close. Gotcha. It's not transitive either. Case closed. All right, for our last section, let's talk about a very common trap, one that catches a lot of people out. We'll also quickly summarize our key rules of investigation to make sure you have everything you need to solve any case that comes your way. Now, look at this one very carefully. This is a classic trick question. Our set is 1, 2, 3. And our relation has just one single pair in it, 1, 2. The question is this relation transitive? Think about the rule, the exact wording of the rule before you answer. And the answer, which might surprise you, is yes, it is transitive. And here's the aha moment. Remember, the transitive rule starts with if you have AB and you have BC. Well, in this case, we have our AB, that's 1, 2, but do we have a second pair that starts with a 2? Nope. The chain never even gets started. Since that first if condition was never actually met, the rule was never broken. The property holds true by default. It's kind of like being innocent until proven guilty. We couldn't even put it on trial. So these are your golden rules. Let's lock them in. For reflexive, you have to check every single element. For symmetric, if you find a pair, you must find its reverse. For transitive, if you find the two-part chain, you must find the shortcut. And never forget your 2 secret weapons, the gotcha rule for proving something is false, and the subtle but powerful no-chain rule for those tricky transitive cases. And to wrap this all up, I'm going to leave you with one final case to ponder. Think about the set of all people in the world, and the relation is a sibling of. Is that an equivalence relation? Run the tests. First, is it reflexive? Are you your own sibling? Probably not. Second, is it symmetric? If I'm your sibling, are you mine? Seems so. And third, is it transitive? If A is B's sibling and B is C's sibling, is A automatically C's sibling? Think about it carefully. The answer to that last part might not be as simple as it seems. Have fun with that one.